Okay, so in this video we'll be looking at the properties of exponential functions. So to start things off, just a quick little easy table of values using two different functions, 3 over 5 to the power of x, as well as 5 over 3 to the power of x. And then when we were completing this table, just taking that base and then using our exponent of x every time. And we should notice a pattern here. For 3 over 5 to the negative 4, remember the negative exponent tells us that we're going to flip things. So this should have the same answer as 5 over 3 to the 4, which it does. So let's just make a graph of these and see what happens, and then we've got something to talk about for these functions. So for negative 4, we're at about 7, almost 8. Negative 3, about 4.5. Negative 2, we're at 2.7, negative 1, 1.6, then 1, then 0.6, 0.36, and we know we get lower and lower until we've got that asymptote. So if we connect these, we've got a pretty smooth curve here. So this is f of x equals 3/5 to the power of x. And let's do the same thing on the other side. With negative 4, we've got a really tiny number, which is okay. For negative 3, getting a little bit bigger. Same with negative 2, negative 1. And then at 0, we get 1. At 1, we've got 1.6. At 2, 2.7. And then we'll just keep continuing this on again. Same idea. Cool, so g of x is 5 over 3 to our exponent x. So what makes something an exponential function? Well, exponential functions are always going to have this type of shape. Their graphs are always going to have this kind of increase, like 5/3 to the power of x, or this kind of decrease, like 3/5. So with our exponential functions, we've got b to the power of x. And x is the exponent. That's different from our, exponent. That's different from our quadratic functions, from any of our other ones. X was always the root or something else. Now we've got this one extra restriction that our base cannot be, or our base has to be greater than 0. If b is just 0, 0 to any exponent will always be 0. And then if b is negative, we get some really funky stuff. Let's say if we've got negative 2 to the power of x, well, for certain exponents that might be a positive answer, and certain exponents that might be negative. So b is always positive, just to make sure that we've got the smooth curve. So this makes sure we've got our curve is smooth. Now, regardless of our base, our domain will always be the same. Your domain is just xer, because there's no restriction for what exponent we can put in. We can raise whatever our base is, we can raise that to negative exponents. We can raise that to positive exponents, to decimal and root exponents. So there's really no limitation on what our domain is. For our range though, so our range, we've got yer. And we notice from our graph that both of these have an asymptote. Our red one has an asymptote on the left, blue has the asymptote on the right. But both of these functions have an asymptote along our x-axis. So whichever way our function is going, either way it's coming in towards your x-axis. And that kind of fits with our values as well, right? As big as we make this exponent, we're never going to get to 0. Or as negative as we make this exponent, negative 10, negative 100, whatever, this is never going to reach 0. So our restriction for the range is going to be y has to be greater than 0. Not greater than equal. So just watch out for that. Okay. Now intercepts, our x-intercept doesn't exist. We've got an asymptote here, so no x-intercept. But our y-intercept for both cases is 1. And then the asymptote that we've got is the x-axis. And that's the equation y equals 0. Our asymptote is this really nice horizontal line through a y value of 0. Okay, so our graph is coming in towards that asymptote. Now, the intervals of increase and decrease, that's going to be different depending on if it's exponential growth or if it's exponential decay. So our red graph was growth, and that graph is always increasing. We go from really small values, and every step forward here is increasing. Now let's think, when are we going to have exponential growth though? Well, for the next number to be bigger, we need to multiply something more, like we need to basically multiply by something more than 1, because we need it to grow. So our growth happens when b is greater than 1, and in that case we're always going to have an increasing function. And then on the other hand, if we have exponential decay, like our blue graph, smaller and smaller each time, that's when our base is between 0 and 1. And that case will always be decreasing, always getting lower. So we can tell the intervals of increase or decrease just based off of the base, just by figuring out what number is being raised to each exponent. Cool. So those are some of our properties. So now some interesting stuff about the tables of values. So the type of function can be figured out based off of looking at our y values. So polynomial functions have constant differences in our y values. So that's when we subtract each pair. Polynomial functions, just to note, have natural number exponents. So these are whole and positive. So root x is not a polynomial because that's x to the half. 1 over x also does not count as a polynomial because it's x to the negative 1. But polynomial functions might be something like this, 2x, maybe x squared. If you're taking advanced functions, you might look into x cubed and x to the 4. Even different variations of that, maybe x squared, x cubed, plus x minus 1. That's considered a polynomial as well. So let's just complete these tables and see what happens. So using the x value of -3. So 2 times -3, -6. Just gonna complete this. Now our first differences are coming from subtracting our y values. You have to make sure you do the bottom minus the top. So for each pair, I cut that off there, bottom minus top. So for each pair that we're looking at, we take the bottom number, subtract the 1 above. Because we're trying to see what's the change from -6 to -4. So when we subtract these, we get 2, and that looks good, we're increasing by 2. So let's just repeat this a couple times. -2 minus -4, again, is 2. 0 minus -2, also 2. 2 minus 0, 4 minus 2, and 6 minus 4. So a linear function, something that's straight, like this line, y f of x equals 2x, is going to give us a really nice straight line. That should be all my points. Yeah, we can tell this guy is going to be a straight line just based off of having constant first differences. So a line, a linear function, constant first differences. All right, let's see what happens with x squared. So we're taking -3 and then squared. -2 squared, -1 squared. Continuing that. And let's start with our first differences also. So 4 minus 9, -5. 1 minus 4, -3. 0 minus 1. 1 minus 0. 4 minus 1. And 9 minus 4. Yeah, messed up there. There we go. 9 minus 4 is giving us 5. So first differences. So we see from this table that our first differences are not constant, therefore it's not going to be a straight line. Well, let's check our second differences. We can subtract these guys now. So let's go same idea, bottom minus top. -1 minus -3, 1 minus -1, 3 minus 1, and 5 minus 1. And we get +2 for all cases. So these are our second diffs. So in a quadratic function, we end up getting that the second differences are constant. And a really cool fact about polynomial functions is if you don't know what type of polynomial it is, well, you can keep taking your differences, and as soon as all your differences are the same, that tells you the degree. So because the second time we subtracted, we got the same number, that tells us our overall exponent is going to be 2. And let me do a quick sketch here just to show you that we've got a really nice quadratic. Woohoo! Okay, so your differences will be constant only in polynomial functions. Let's see what happens with exponents. Now I've done the same equation twice. F of x equals 2 to the power of x. And I'm just going to complete this real quick. It's the same graph in both tables. Or sorry, the same equation in both tables. And what I want to try and see is, do our finite differences tell us anything for exponential functions? And if not, what can we do instead? So first up, let's see our differences. 1/2 minus 1/4 is 1/4. 1 minus 1/2 is 1/2. 2 minus 1 is 1. 4 minus 2 is 2. 8 minus 4 is 4. So nothing really interesting there. Let's try again. 1/2 minus 1/4. All right, that's 1/4. 1 minus 1/2. 1/2. 2 minus 1. 4 minus 2. All right, nothing really. What if we go again? Okay, 1/4. 1/2. 1. Okay, nothing's happening, and I'm really close to running out of numbers. Ah. So our differences aren't really telling us anything here. We just keep getting the same values every time. 1/4, 1/4, 1/4, 1/2, 1/2, 1/2. So differences don't really tell us that it is an exponential function or not. So what I want to try in this side instead is calculating the ratios. So that means dividing. And let's still do the same, bottom divided by top. Okay. So this will be our first ratio. So let's do 1/2 divided by 1/4. 1 divided by 1/2. 2 divided by 1. 4 divided by 2. And 8 divided by 4. Let's try some mental math. Dividing by fractions, we're going to flip the second guy. 1/2 times 4/1. All right, our numerators multiply to give us 4. Denominators are multiplying to give us 2, and then 4/2 is a nice 2. All right, that's pretty good. 1 divided by 1/2, same thing. This guy flips. 2, 2, 2, 2. Okay, finally we got somewhere. So if you find that your differences aren't getting you anywhere, try dividing, because if your pairs of terms are dividing out to the same thing, that's going to tell us it's exponential. So the relationship between the type of function and its corresponding finite differences, whichever differences are the same, tells you the degree. That's your overall or your highest degree or exponent. So your overall degree or highest exponent. Now because this is differences though, please make a note, this is going to be for polynomial. Okay. And then the relationship between linear, quadratic, and exponential functions. Linear and quadratic are polynomials. They have constant differences. Whereas an exponential function will have constant ratio. Oops. Okay, so if we were to divide out, as long as you're dividing out pairs in order, going bottom minus top, if you get the same answer, that tells you it's going to be an exponential function. All right, just to sum things up real quick at the end, so our exponential functions are always going to be of the form y equals b to the power of x. So b can be any real number, our base can be any number. X always has to be the exponent, and sometimes you've got a coefficient in here, a. So sometimes we'll have y equals a, then b to the x. So if we have a coefficient there, that's a possibility, even though it is a transformation. We always have to assume base is going to be greater than 0 so that nothing funky happens. And then our overall characteristics, well, if our base is greater than 1, so in that other one that we looked at, 5/3 is greater than 1, we're going to have growth, which is always increasing. For bases between 0 and 1, we've got decay. So again, back to here, 3/5 to the x was a nice decay. And then without any transformations, we've always got a horizontal asymptote at your x-axis and a y-intercept of 1. And then we set our domain and range before. Domain was xer and then yer, such that y is greater than 0. All right, and that's about it for exponential function properties. Thank you.